your midterm, and then maybe the next week I will have a little bit short time to discuss about the midterm exam, how you can prepare for the midterm exam. Okay. So today we are going to discuss about the last topic. I think that we have one more deadlock management in chapter 7, so pretty much up to chapter 6. So in this chapter we will discuss about one of the important algorithm in the process management, that is the CPU scheduling. So last class we mostly discussed about the process synchronization, because the operating system can create the multiple processes for their cooperation. That's the user. The main problem is what if we have the shared resource at that time. So many processes are competing with the racing with the other processes to get the permission of the resource. So that is the motivation of the synchronization. So we need to address that problem. Basically, we can use a lock. So a process who can acquire the lock can enter we define such accessing the shared resource as the critical section. So whenever a process use the shared resource that may cause the race condition, then operating system or the hardware provide the data structure for the process. That's the critical section. So operating system or the software need to provide how to control, acquire the lock or release the lock. So we define the requirement of such a synchronization problem solution. One is a mutual exclusion, which means it's obvious only one process can enter critical section. In other words, only one process can access the shared resource. So that is the mutual exclusion. And second is progress. Progress, no matter how the progress is described or defined, you can remember. So no deadlock free, which means it will not be stopped. Okay? Because many processes are racing for the shared resource, there might be possibility the certain process cannot enter critical section. Okay? So if we can address such a problem, which means if anytime at least one process can enter critical section, that is the progress. That is only for the process itself. Then the third requirement is the bounded waiting. Such a waiting should not be forever. Okay? So which means it's a starvation free. So if you remember the deadlock free and starvation free, no matter what algorithm you have, you can prove whether the algorithm can satisfy with the synchronization problem. For example, in your quiz 3, there's the algorithm which is first. Nowadays, we don't use the Becker's algorithm, the SADs, but it's the first commercialized synchronization solution. It's similar as the Patterson solution. Okay, but in Becker's algorithm, we also use the turn and flag, the two shared variables for each processes, and then the flag shows whether that process would like to enter critical section or not. Turn means whose turn is who are using the critical section nowadays. This is basically the same idea as the Patterson solution, but it can provide another the algorithm for the entry section. That is, once the process enter the entry section. So after you set the flag, okay, then enter another while loop, busy waiting, to wait for another process who are in the critical section, then eventually out of the critical section, then change the turn value. Okay, flag is changed because right now it's the room to enter the bathroom like that. Okay, so it can preserve the progress as well as the bounded waiting. Okay, that was the your phase 3. Then after we solve the problem of the synchronization, so we have the multiple processes. So we are able to create the multiple processes, and we can address the problem of the synchronization issue, race condition. Then still we have very limited resources. Always in the operating system, when you build and design the operating system, main issue is we have the limited resources, but we have the many consumer like the processes. That is always a problem. So we need to address the problem of the synchronization. We need to, but still we have the limited resource. So to address such a problem, so whether we can fairly manage the resource for the multiple process, that is the CPU schedule. So we try to schedule. We try to assign the certain amount of the resource for the specific processes. Okay, so it's like when many students would like to see the advisor. Okay, so suppose that we have only one advisor, but the many students who would like to meet the advisor. But think about the advising time. Can we increase the advising time or decrease the advising time? No, the advising hour is the 2 hours, is the same. Okay, but we try to maximize the such a advising time utilization. Okay, the maximum is 100%. Okay, just like that in the operating system, we try to maximize the utilization. Actually, not like the 100%. In case we have the 100% utilization of the CPU, that means mostly it's something the infinity loop or the while loop. So anyway, so our goal is to maximize such a utilization. With what? With the satisfaction of the process. Okay. For example, if only one student take all the time, 2 hours of the advisor time, all the other students will complain. Even though we have the 2 hours maximizing the advising time, is not fair. Okay. So some of the students are urgent for the registration that need only signature. It takes just a couple of seconds. But some students need more time to discuss about whether I need to change the major order. So depending on the requirement of the process, we can consider the different algorithms. So what can be the easiest and simplest way to schedule the many process or the many students? So first come first. As you can see in the first come first, it's not bad algorithm. Okay, so first come first serve is also part of the priority based. Any operating system algorithm that compete with other the consumer and the producer is always based on the priority based. In case of the first come first serve, what is the priority? Arrival time is the priority. Okay, so if the student come to the advisor office, that is the first choice. Then second and third. Problem, if the first process takes a long time, all the other students are waiting, right? So, for example, all the other students, the 10 or the 90 students, they need only just a signature. So the student need only a couple of seconds, but because of the first student, so many of the short period time is called the CPU burst time. So the process that need a short CPU burst time will be hidden by the long processes. So first come first serve, even though that is actually fair because it's the first alive, but it may have the issue in case we have the process that need the very short CPU burst time. So what can be the next solution? We can consider different priority. So amount of time that process need. If we CPU, the process need short amount of CPU time, we can give the higher the priority. For example, in case of the advising, the professor can check the who need just the signature. Then I can give the signature first. Then we'll meet the another student who need shorter time. Okay, so that is the shortest job. Okay, the CPU scheduling. Okay, very simple. And what else?
Time sharing.
Time sharing. So we can actually divide the advising time by 5 minutes, 5 minutes, 5 minutes, 5 minutes. Then we can assign that time for each student, maximum 5 minutes. Okay? Then if you need more time, and next round, which is called round robin. So that's another solution. So we will see that today. So basically the algorithm itself are not very complicated as we just discussed, but based on the process structure and then need the CPU burst time, we will discuss about what kind of the CPU scheduling algorithms are used in the operating system. Okay. So basic idea is whether we can maximize the CPU utilization for multiple processes. So we will discuss about the various CPU scheduling algorithms here. Okay, then eventually we will evaluate such an algorithm, which one is good, which one is not, and whether what is the pros and what is the cons for each algorithm. Okay, then we will examine the CPU scheduling algorithm for each the several operating system. Probably that include the Linux system, based on the POSIX, the library, and the Windows, and so on. Okay. So this is the basic idea. By the way, don't be confused with the other scheduling algorithms in operating system CPU scheduling algorithms. There are many similar scheduling algorithms. So, for example, think about the postman, like the UPS delivery system. UPS delivery system, for example, in my town, my house is located at the corner of the two streets, and it looks like like the Manhattan, but it's a rural area. So postmen usually come to this way and deliver like this. And so some of the postmen like the main street first, okay? Then going back and forth. There are various different ways. So depending on the route, it may take a longer time, may take a shorter time, may take a longer distance, sometimes it's a shorter distance. So depending on the algorithm, the algorithm can take the longer time or shorter time, longer distance or shorter distance. However, think about another scheduling is, so for example, the ticket booth. So when you go to the baseball game, so there are several booths. So suppose that we have the 3 booths, and sometimes the line is for each booth there is a line. Okay, so we have 3 lines. So if the line is not very fast, it takes a longer time. So you're lucky. So to address that problem, so we have the one line over here. Then for each we can, whenever the booth is available, we can assign. There might be different algorithm, different scheduling algorithm to sell the ticket. However, selling the ticket is that, so can we increase the time or decrease the time? If we consider the same amount of time for each ticket is selling, it will take the same time no matter what algorithm you use. Okay? So we cannot change the time. Similarly, in the CPU scheduling algorithm, so as we discussed before, this is a CPU time. Okay? Whether or not this CPU is working, this CPU is processing any instruction or not. Anyway, this is a time. So even though you have the perfect, the CPU, I don't know what is a perfect yet, but if assume we have the perfect, the CPU scheduling algorithm, but we cannot stretch out the CPU time. We cannot shrunk the CPU time. It's a CPU time, is a CPU time. Okay? Our goal is to utilize all the CPU time as much as possible. Ideally, 100%. However, we are not going to consider the while for busy waiting that may cause 100%. Just ideally, 100% is the best case to utilize the CPU perfectly. So this is our goal, to maximize the CPU such a utilization. Then how can we maximize such a CPU utilization? Let's go back to the basic, the process, the operation. What process is doing? First, when process is created, it will enter ready queue. Okay, this is the process state. So then, if the process is selected, that selection we will discuss today. Whatever the algorithm, let's say this process is selected by the CPU operating system, this will be
Running state.
the running state. It's running. It's processed by the CPU. Their instruction will be processed by the CPU. Then, what kind of instruction we have? So first, the most popular instruction is move. Move the data in the memory to address to the register. Then the data in the register will be processed like the increment or add, subtract, depending on your CPU processor. There are several instruction operation. So that is the job of the CPU. So CPU can process, but this is the thread of the instruction. Some of the instruction need to access data from, for example, hard disk drive, your file system. Okay, read the data, then bring the data to the through. When you read the data, you need to interrupt, then ask to the controller. Okay, controller receive the address. Okay, so we will discuss details later in the I/O management. It's a high-level address, like the integer I. Then it has the sector number and something like that. Then this controller know using that address how to find the data from low address. Okay, like the cylinder number and the sector number and so on. Then return when this one is the when you find the data from your hard disk drive or file system, then this controller inform to the operating system, I'm ready to return. Meanwhile, at that time, so asking the data and returning the data, what the CPU can do?
Put the process in wait state.
Nothing, actually, because there is no data. You cannot operate until you get the return the data. So CPU cannot do anything. So you operate. So that is the operation of the CPU. Then at this amount of time, you cannot do anything. This is called I/O wait. So it's a waste of CPU time. So how can we utilize such an I/O waiting time? We can give the chance to the another process, like for example, when I advise a student, so I'm discussing with this student and he is asking waive the prerequisite. I have transcript, but I do not have the transcript, so I'm asking to the secretary to find his file. So it takes some time, so I'm ready. Then it's a waste of my advising. Why don't you wait outside of my office, then I can meet the next student. Okay, exactly saying the idea, so we can give the chance for the other process is using the CPU resource. Okay, then at that time, the process that need I/O operation will change their process state into the wait. Okay, queue. Then if this one return inform through the interrupt, so I got the data, then the inform to the operating system, then this one will move back to the ready queue. And meanwhile, the dispatcher will select the next process, then we can utilize this CPU resource for another process. So we can divide into two folders. One is the CPU burst time and another one is the I/O burst time for the processes. So basically two parts, the CPU burst time and I/O burst time. So during the I/O burst time, it's just nothing, it's wait in the wait queue. Okay, so we try to give the chance to access the CPU resource for another the process. That is the idea of the CPU scheduler. So that it will be managed by sometimes it's called the dispatcher. Okay, so if you take a look at this one, so x-axis is this is called the burst time. Burst is an amount of time that need the CPU or I/O. So mostly it's a microsecond level. So 10 or the 20 microseconds is CPU burst time or I/O burst time. So if we take a look at such a I/O burst time by the frequency. For example, here, if the burst duration is the short and is the high, the requested, that's mostly it's the I/O bounded job. And CPU bounded job need the longer time of the CPU, because definitely this CPU job need more CPU time. Okay, so this is a CPU bounded job. So we try to utilize this amount of time for CPU bounded job for another process. That's the idea of the CPU scheduler. So CPU scheduler, as we discussed before, there are different types of the scheduler in operating system: long-term scheduler and short-term scheduler, and the midterm, but midterm is mostly swap, so we don't consider seriously. So long-term scheduler, we are going to select the process job itself. Okay. Then on the other hand, the short-term scheduler is for the selected job, selected process, we try to give the chance for each process to access the CPU resource. It's usually takes time very quickly. So because that is called the short-term scheduler, in this the scheduling algorithm, we are going to discuss about the short-term scheduler. Okay, how we can manage such a processes in the ready queue. Okay, in the ready queue, we are going to select one of the process based on our algorithm that we are going to discuss today. Then, first, no matter what algorithm we are going to use for the dispatcher or the CPU scheduler, when this algorithm will be invoked, when this algorithm will select the process every time. So there are different cases. So for example, here, one is, this is a running queue. So if the process is moving to the wait queue from the running queue, there's no process. So CPU scheduler need to select the next process. This is one case. And second case is from sometimes a certain amount of time the process in the running queue will back to the ready queue. Okay, a ready state. Okay, it's not queue. A ready queue or ready state, that is just so there's no process in the running queue, so the CPU scheduler or dispatcher will select another process. This is case 2. And also, process in the wait queue, in case the controller return the data by the interrupt signal, so then CPU scheduler need to select the next process. It can be this one or not. However, this dispatcher need to know this process is ready to be the process, the next instruction. So in this case, the CPU scheduler will learn their algorithm to select the next process. So from wait queue and to the ready queue, and also terminate. There's no process in the running state, so we can select the next process. At that time, this one and this one, and running from the running to the wait or the terminate. This case is called the non-preemptive. All the other cases are preemptive. So what does that mean? The preemptive or non-preemptive. Preemption means kind of priority. Okay, keep the first. So I keep this one. So I have the first priority one. I have the preemption of this choice. Even though I leave when I get back, so I have the permission to keep this one first priority, something like that. Is a preemption. However, non-preemptive means, so once I take this seat, I try to keep this seat until I finish my job. Okay. Otherwise, if I leave in the middle, that's done. So I do not have a preemption for that seat. That is a preemptive, and that is if not guaranteed, that is a non-preemptive. Okay. So which means the 2 and 3. 2 is go back to the ready queue, or the 3 is from the wait to the ready queue. So ready queue, so then they are, so I have used the CPU resource before. Okay? So I try to continue the processing. So it's a preemptive. At that time it's not guaranteed that you are the next one. It depends on the algorithm, but I can continue to use, okay, that resource. That is the preemptive. So in CPU scheduling algorithm, there are two types of the scheduler. One is a preemptive. Preemptive allow to stop and continue, okay? So that is a preemptive. Non-preemptive means, so if I leave this seat and no chance to retake, I need to start again from the beginning. Okay? So that means the non-preemptive algorithm is once process takes a CPU resource and keep it until the end of the instruction. Otherwise, you cannot restart it again. That is a non-preemptive. For example, in this case, once you leave, it's done. Okay? So you cannot restart it. So keep in mind in the 4 cases, the CPU scheduler will be activated. Run their program. Okay. Then the dispatcher is an operating system, the module to implement such the CPU scheduling algorithm that include what happened when CPU scheduler dispatcher select the next process. We need to do the context switch. What is a context switch? Context switch, how the CPU can process the operation instruction. You need register. And all information about the process, the CPU should know. Okay? So where can you manage such information? PCB. So all PCB information will be changed. That is the context switch. Okay? So that will happen by the dispatcher. And this CPU scheduler is for user mode. Do you remember the operating system has two dual mode? One is the user mode, your application code. Another one is kernel mode. Kernel mode is for the system library. Okay, who is in charge of that kernel mode? So operating system. So you don't have to. Your the user mode application and the instruction will be managed by the CPU scheduler. Okay. However, it is true when even though you have the perfect CPU scheduling algorithm, that will take a time to select the next process, right? And there might be time for during the context switch because the context switch need input and output. I/O required, so it takes a time. That duration of the time between the one process to the next process, that is called the dispatch latency. Okay, so dispatch latency may cause the system degradation. So you need to consider when you manage the real operating system, if the dispatcher select the next process frequently, you may cause the system performance down. So dispatcher latency is another issue when you consider the scheduler algorithm. However, in the practice of the CPU scheduling algorithm, we are not going to consider dispatcher latency, okay, which means right after the CPU schedule select, right after the current process, the next process will take over the CPU time. Okay. Then, I just say perfect, good, the CPU scheduling algorithm will maximize the utilization. But as we know, the 100% is not always it's not guaranteed this is the best algorithm. So our goal is to maximize the utilization of the CPU resource. That's not enough. We need to satisfy all the students during the advising time. So there are different criteria to judge whether CPU scheduling algorithm is good or not. The first, CPU utilization, so as busy as possible. Okay. Then throughput is number of process in the certain amount of time, like the 1 day or 1 hour or 1 minute, how many processes, how many jobs are completed. Okay, that is called the throughput. And turnaround time is average turnaround. First, the turnaround time is total amount of time, okay, to finish one process, one job. Okay. Then, if you have the multiple job, multiple process, what is the average turnaround time, okay, to finish all the job? That is the turnaround time. So this throughput and turnaround time is good for what? To judge batch job. If your system focus on the batch job, like the data warehousing system or the housekeeping job or the removing the bunch of the temporary file on your operating system, you can judge your scheduling algorithm using such a thing. And waiting time. Waiting time is if you have the process like the P0, so it's a started time 0 and running and finished 100. However, during that time from 0 to 100, so P0 cannot take all the time CPU resource. Like for example, wait 10 the microsecond and take the CPU and 15. And wait until the 50 and take the 10 microsecond from the 50 to 60 and wait, and 90 to 100, and finally this is waiting. So this amount of time, like the 10, 35, and 30, so this is the 75 is the waiting time. Okay, even though it takes in this case, what is the turnaround time? So 0 to 100. Okay, so it's 100. However, so it doesn't consider the waiting time. So if you consider only the waiting time, that is the waiting time. Then you can average it. In case of the multiple process, you can average. You can judge whether this system has a lot of waiting time. Then may the reasonable if you judge whether advising service is good or not. So if you wait the longer time, this satisfies. Okay, it's the same idea. Then another criteria is response time, which is the most popular one. The response time is this one, only this one. Starting time to first response time. No matter how long this process, the wait, or no matter how long it takes to finish, it doesn't matter. Just the time between execution and the first response. This is important for what? Online transaction processing. Like think about the web server, web services. If it takes to open the first page, if it takes I'm not sure that nowadays, but when I learned the first time the web service or the web browser, if it takes longer than 7 seconds to open the first page, the customer will leave. So it is very important to provide less than 7 seconds the response time for the first page of your website. Because of that, some of the web pages have the very simple, the first page, okay, for the very fast response time. Or sometimes you can send the text data first, then all other images or video or the big size of contents will be followed later. Okay, so that is the reason sometimes you can see only the text, the message when you open the file. So to provide faster response time. So fast response time is very important to judge the algorithm. Then we can make the average in case of the multiple processes. So mostly we are going to use such a response time and waiting time to judge the algorithm in the CPU scheduling algorithm. Then our goal is maximize the CPU utilization and maximize the throughput and minimize turnaround time and minimize the waiting time and minimize the response time. Okay, so these are the algorithms that we are going to discuss. So we already see the first one. So first come, first serve. What is the priority? All of these are based on the priority, actually. For example, the synchronization algorithm, we can understand the synchronization solution as a priority based. Similarly, that is the easiest way for computer data structure. Which one will be selected? It's based on the priority. The problem is what kind of a priority you are going to use. So in this time, priority is first come. So arrival time. Arrival time is the priority. Then it has the problem of the short amount of time, short CPU burst time. The processes, they will be hidden by the long time, the processing process. So to address that one, we can consider shortest job, small CPU burst time, the job first. That is in this case, what is the priority?
Very small time.
It's the remaining time. Okay, what is the not remaining time? It's the CPU burst time that need to finish the job. Then, if we process here, in this case, 15, I think that this is a 5. 5, 10, 10, 25. So it needs 25 the microsecond, 25 CPU burst time. But at this time, only remained is 10. Okay, so why don't we consider not the beginning CPU burst time, but the remaining time? So that will be fair. So in this case, we can consider remaining time as the priority. Which one is the shortest remaining time? So that is called the shortest remaining job first. Then explicitly we can assign the priority, like the Windows. So if we open the task manager, so you can select the priority of each process, normal, high, or low, like that. So that is the priority scheduling. That is the most popular one in the operating system. Then we have, as we discussed before, why don't we slice the time that assigned for each process fairly? Okay, then if so still you need the CPU time, and next round, that is a round robin. Then, none of this can solve all the problem. So just like the other solution, why don't we combine like the hybrid? So that is multi-queue and multi-level feedback queue. So today we are going to discuss all of this, hopefully. So for the CPU scheduling algorithm, we are going to use the Gantt chart. Gantt chart is kind of the bar graph. So along the time, so this is the time, okay? Then we are going to assign the process. So this means process 1 takes the CPU resource from 0 to 24. The unit of the time can be microsecond or nanosecond or the hour. So I'm not going to use any specific unit of the time. So, but you can imagine whatever the unit. So this is a 24 time slot. So P1 takes the 24 time slot, then followed by the P2. P2 is a 24 to 27, and lastly the P3, so 27 to 30, like that. So this is called the Gantt chart. So we are going to use this Gantt chart to understand the CPU scheduling algorithm. And also, there are several ways to understand or to evaluate the CPU scheduling algorithm. So one of the popular way is the deterministic solution. That means we can provide such a process state, okay, process data. So for example, P1 align the time 0 with CPU burst time 24. That means P1 need 24 time slot to be completed. Okay, it aligns the 0. So we provide such a process information. Then run your algorithm using such the process state. Then compare with the other algorithm, whether this one is better or whether this one is better. How can we judge? Using criteria that we discussed, like the waiting time or the CPU burst at waiting time, and response time, or the throughput, or something like that. So using criteria, we can judge using this one. So we are going to use such a deterministic evaluation method to understand the CPU scheduling algorithm. This is the first one. First come, first serve. So we are going to use the arrival time for that. From now on, I strongly suggest this one is the easiest one, so you can understand because you are so smart, you can understand that directly. But I strongly recommend to manage the ready queue and running queue. Running is not a queue, it's a running state. Which one is running? Okay? Manage. So in your project 1, you are going to implement the CPU scheduling algorithm. So it's the same thing. You can just convert the CPU scheduling algorithm that we are going to discuss right now into the programming. Okay, that's it. So first thing is you need to understand. In the project 1, so you need to manage such a running at the ready queue and the run state, which process is running. Otherwise, it can be, this one is the easiest example. So you can understand intuitively. However, if you have the more the process, the list in the process state, it will be more complicated. So strongly suggest to manage that one. Then we have the CPU Gantt chart from 0 to something we don't know how much is it. Then first P1 is alive. So when P1 is alive, is in the ready queue. Okay? With what kind of information we have? Arrival time and CPU burst time, 24. What is this, by the way? P1, 0,24 in terms of a process data structure. It's a PCB. This is a process control block that describes your process. Okay? So in your project 1, you need to define your PCB. So the I know there are a bunch of the source code for the implementing such a first come first serve is very popular, but I'm going to take a look at whether you define process control block or not. Okay, clearly. Then whether you have the running queue or not, the ready queue or not. Whether you have the run state, which means you are going to manage in your PCB, you need to have the process state. Okay, then you have the ready queue. You can use the queue structure to manage the number of processes who are waiting for the CPU resource. So this is a simple PCB that includes what? The arrival time and CPU burst time. Okay, then do you remember when dispatcher is invoked?
Yes.
This also, obviously, if there is a new process, and also obviously every the period time. But we are not going to consider such a period time. But if there is a new process like this one, the CPU scheduler first time run. So this one is the only process we can select. So P1 is a select. There are two algorithms in the CPU scheduler. One is preemptive. Another one is non-preemptive. What is the difference again?
Preemptive can restart from the same stop.
You can preserve, you can guarantee such a previous state. Non-preemptive, no. If the process stop, it's gone. Okay, which means the process, once process is started, it should be completed. Okay, because you cannot guarantee preemptive. Okay, so first, this is a non-preemptive solution. Non-preemptive, so we need to complete until the end of the process. Meanwhile, process 2 is, we need to update this one. P1 is here, 0, 24, right? Also, this is the current time. So current time 0 is selected. Then P2 is arrived, time 1. So time 1, P2, and arrival time is 1, burst time is 3. And P1 is still in the running state. Because it's non-preemptive case, non-preemptive can take the resource until the end of the process. Then, meanwhile, process 3 is alive, the time 2. P3 is the time 2 alive, and CPU burst time 3. Then, time is going on until 24. 24, so this is the 24. This will change into terminate. Okay? In the terminate, it will be invoked. So, CPU scheduler will select the next process. What is the priority? Arrival time. You can check the arrival time. Which one is the earliest one? Process 2. Process 2 take the CPU resource until the end of process. That is the 27. So 27. P2 is here. And 27 is terminated, no other process, and P3 will be selected. It's the last one, so P3, so this is 30, so that is the first come, first serve algorithm. I know without this one, it's easy, but for the next and the more complicated algorithm, I strongly suggest, not strongly, it's mandatory in your program to manage the time, definitely, and the ready queue and run state in your PCB. So you need to create such a PCB process control block that can manage the information. Then we try to evaluate this algorithm in terms of waiting time and the waiting time. So for the waiting time, we have the 3 process, P1, P2, P3. What is the waiting time of the P1? So 0. No wait. And what is the waiting time of P2? It's started 24, arrived the 1. So 24 minus 1 is a 23. P3 started 27, arrived at 2, so it's a 25. So then, average waiting time is 0 plus 23 plus 25 and divided by 3. That is the 16. This is the average waiting time. Okay. What about the response time? You can calculate the first response. That will be the same as this. Why? It's a non-preemptive case. Once it started, it's completed. The waiting time and the first response time will be the same because there is no waiting time in the middle. So this is also the average, the response time. So that is the 16. Okay. Any questions? Definitely, the CPU scheduler is the part of your midterm exam. As I said, the midterm will be March. It's a 10th, so in the classroom. But I'm thinking the room that is much bigger than this. Okay, I know, I believe that you guys, but to be fair, sometimes the student complain it's too close. Okay, so I'm looking for the bigger room. But anyway, that will be the same. The time, but maybe different location. I will let you know. And the midterm will cover up to the CPU scheduler. Okay. The next, before that, so check whether what is the characteristic of the first come first serve. Definitely, it's a simple and fast. Select one because we can just consider the arrival time. Also, we don't have to sort looking for this one because it's a queue. So automatically first come, first serve. So we can use it's very fast. As you know, the queue structure is one of the fastest. The structure is O over 1, the complexity. Okay. Problem? As we discussed. So for example, this is the one. Why don't we change the arrival time and P1 into, so P2 arrived the first and P3 is the next and P1 is the last one, okay, with the same CPU burst time. So I don't have to use again, just to quickly see the Gantt chart, P2, P3 and P1, okay? You can understand easily. Then what is the average time? P1 is started at 6 and arrived at 0 is a 6. And P2 is a 0. And P3 started 3, arrived 1. So it's a 2. So total 6 to 8 divided by 3 is a 2 point something, right? Why is not?
Process P1 arrived to 6.
P1 is arrived 6 and 2, so it will be 4. It's a 6, it's a 2. Okay? Previous one is a 16. It's the same CPU burst time. Okay? However, depending on the order of arrival time. So their average time and response time are hugely different. That is because of what? It's called the convoy effect. Convoy effect means short process will be hidden by long process. It's the same as the advising example. So that is the problem of the first come first serve. It's not very suitable for time sharing operating system. That means it needs faster, quick the response time. Okay. So to address that problem, why don't we consider CPU burst time for each processor? No matter when there is allowable, we'll consider the CPU burst time. So we can consider both the schemes, like the non-preemptive cases and also preemptive case of the shortest job first. Okay, we will see the first, then discuss the difference later. So we are going to manage the ready queue and run state, and time is a 4 processes, P1 alive, time 0, it needs 7 CPU burst time. P2 alive, the time 2, and with the CPU burst time 4, and so on. We have the 4 processes. So first we are going to consider shortest job first with non-preemptive case. Non-preemptive means we cannot guarantee that we cannot preserve the previous state, which means once it is started, should be completed, like the first come first serve. So P1 is alive. So P1 is a time 0. P1 has the 0 arrival time and CPU burst time 7. Then it will be selected right away. So P1 is here. Okay, then P1 move to here. P1 is a 0 and 7. Then P2 is alive at, no, not this one. P2 is alive at time 2. So 2 arrival time and CPU burst time 4. Then, do we need to select the new process here?
No.
No, because it's a non-preemptive. In case of preemptive, we need. We will see the soon such a preemptive, but if this is a non-preemptive, so we cannot guarantee the previous one, previous state. So we need to terminate the until. We need to process all the instruction until terminated. Okay, so we have the P2 over here. At time 4, we have another process P3. It's alive at 4 and CPU burst time 1. Do we need to select? No, it's a non-preemptive. So P1 is still running until CPU burst time 7. Not yet. Then time 5, P4 is alive 5 and CPU burst time 4. Okay, so this is a time 5. Then time 7, P1 is terminated. Then dispatcher, CPU scheduler will select the next process. So next process, how can we select the next process? Using the CPU burst time. Which one is the shortest job? So P3 is obviously shortest job, so P3 will be selected. P3 move to the one state. You can change the status of the process using P3. Then this one is a P3. How long? So 1. So time 8. P3 is terminated. This is 8. Then we will select the next one. Which one is the next one? P2 and P4 are the same CPU burst time. So we need a tiebreaker. But for the tiebreaker, we can use first come first serve. Okay? From now on, so do not ask during the exam. Okay? It's the same time. So in case of same time, we will use the first come first serve as the tiebreaker. So in this case, P2 will be selected. P2, 2, 4. Then this is the time until it's the CPU burst time 4, so 12. Okay, then P2 will be terminated. Last one is a P4, it's a 16, and P4 will be terminated 16. That is the final of the Gantt chart. It's very easy. Please try to manage the data structure, just like your programming. In your programming, definitely you need to do that. Okay, so let's calculate the average waiting time. So waiting time of each process P1 is the 0, right? And P2 alive the time 2 and start 8. So 8 minus 2 is a 6. P3 alive the 4 and start 7 is a 3. P4 is alive for 5 and started 12. This is a 7. So average waiting time is 6 plus 3 plus 7 divided by 4. That is the 4. This is the average waiting time. Okay. Any questions so far? Easy? Okay. Let's move to the next one. Preemptive. Okay. So preemptive is exactly same process state, but we need to do the context switch. Okay, we can do the context switch because even though P2 is the start here, we can preserve, we can have the guarantee of the previous state, the preempt. Okay, so any question? Any question? Are you? Yes? No? Okay, so then this is the preemptive. What is the difference? So you said that you have no question. What is the difference between the preemptive and non-preemptive? I'm asking question to you. What is a preemptive and what is a non-preemptive? It's very important for your midterm. Okay? So preemptive means you can keep the previous state, guarantee, and accept the priority of that. Like when you are taking a seat, so like sometimes when you are in the library system is the preemptive or non-preemptive. It's a non-preemptive. When you leave, so you cannot guarantee the seat. Okay? But preemptive case, you can get back to that one. Okay? So you can keep the priority. Advance the preservation or something like that. So that is a preemptive and non-preemptive. So in this case, it's a preemptive, same algorithm. So that's any question? If you have a question, just raise your hand. Okay? We are going to perform the same algorithm, but the difference is a preemptive. So P1 is alive. So P1 is alive, the P1 is here, 0, 7. Then it will be selected. So P1 move to the here, then P1 is here. Okay, this is a time 2. And time 2. Time 2, P2 is alive, right? Even though this one is the same time, so once P2 is alive, then dispatcher will wake up, right? Not dispatcher is waking up first. First, because the P2 alive, as I said, we are not going to consider dispatcher latency. So it looks like the same time, but actually the P2 is alive. Then that causes that wake up the dispatcher. Then P2 is alive here, 2, 4. Then it's a P1 move back to the ready queue. It's a 0, 7. Okay? Now the P1 is the first. Okay? Since the P2 is alive, then the dispatcher is a start. Is using the interrupt. Okay? Interrupt. Then the move back the running queue to the running state to the ready queue. So that is a P1. Many of the students confused why the P1 is not first in the queue. Because of the P2, the P1 is moved back to the ready queue. Okay, this is still 2, time 2. Then process, the dispatcher scheduler will select the next process using what?
Burst time.
Arrival time? No. Consider the CPU burst time. Which one is the shortest job? P2 is a 4. Definitely P2 will be selected. It's a time 2. Then P2 will move to the running state, and this is a time 2. Okay? Any question? Yes?
Why the burst time of P1 still remains 7? It should be reduced to 5, right?
That is the remaining job first.
Yeah, so
but here we are not going to consider remaining job. Instead, the initial CPU burst time.
Yeah, so but when the next process enters, it will check both the times. This time will still be showing 7. So
yes.
It will take the job which is 5.
Yeah, that's not fair. That is the reason we have another algorithm that's exactly same as you suggest. Okay, this one we will consider, because if we consider the remaining job, for example, his question is, why is it still 7? Why don't we reduce by 2? It's 2 is already done. Okay, it looks like the 5. Yes, that's the fair in terms of remaining job. To do that, we need to keep track of the remaining job that's also overhead. Okay, so this is another algorithm that consider only initial CPU burst time only. Okay, so that is the reason it's still 7 instead of 5. Okay, then P2 is running and P1 is the ready queue. Then at time 4, next process, P3 is alive. Here or here?
Down.
So actually it's a queue, even though we are not going to consider the arrival time, but this is a queue, so we will put this one, P3, at the end of the queue. That is the 4 and 1. Okay, then this is the preemptive, so P2 will be end of the queue, like this. Okay, then we need to select
P3.
the one of the process, which one is a shortest step? P3. Okay, P3 will be selected. This one. Okay, then until when? P4. Actually, P3 will be terminated at the same time as the P4 alive. Okay, so P3 is terminated. Then time 5 and P4 is alive with the 5 and 4. Okay, so far so good. Then we need to select the next process using what? Burst time. At that time, our tiebreaker is always first come, alive. First come, first out. That means it's a P2 will be selected. Some of the students use remaining job for the tiebreaker. But here in our algorithm, always we will use first come, first serve. Okay, it depends on the tiebreaker. It depends on the algorithm or operating system they use the different. So actually, the most of the operating system use hybrid or the multi-level. Okay, that means they are using not only just one algorithm, they are using many algorithms, including the priority. Okay, so P2 will be selected this time. So P2 will move to the running state. Okay, this is time 5. Okay, then P2 already processed the 2 CPU time, so it needs only 2 more. So time 7, it will be terminated like this one. Then the scheduler select the next process, that is a P4. It's a last CPU burst time, so P4 will be selected and last until the 11. Okay, so this will be done. And 11, this one is the last one. The remaining, how many remainder? And 2, so 5, so it's a 16. So finally, this is done. So this is a Gantt chart for non-preemptive case with the same processor state. Let's calculate the waiting time. Waiting time is P1. P1 waiting how long?
11 minus 0.
2 to 11. 11 minus 2 is the waiting time of the process 1. Right? And P2 aligned the time 2 and selected right away this time. And P2 wait this 4 to 5. Okay? So 5 minus 4 is 1. P3 alive time 4 is selected right away. Okay? So then there's no waiting time for P3. And P4 alive time 5 this time, but selected the 7, so 2 is a 7 minus 5. 7 minus 5 is a 2. Is there any other waiting time? No, it's a 2. So this is the waiting time. Total, so 12. Average waiting time divided by 4 is a 3. Okay? So this is a waiting time. What about this one? It's a 4. This is a 3. So it provides the better waiting time. Okay? So that is. What about the response time? Let's calculate the response time. Response time of the P1. P1 response right away is a 0. And P2 response to arrive to right away is a 0. And P3 arrive for the selected 4 is a 0. P4 arrive the 5 selected 7 is a 2. So average response time is 0.5. In terms of response time, is much better than this one. This is the same. The waiting time and response time is a 4, but this one is much better. Okay, that's obvious. Think about the advising case. So if I give the signature, but maybe the priority is duration of advising time. So even though I can satisfy with many students for just the signature, but these students are critical for the changing the major. Okay, so it's up to you. So what is a policy? That is a reason for beginning of the operating system class. When you design operating system, first priority is not the algorithm itself. First thing is you need to decide the policy of your operating system based on the characteristic. Okay, so that's the difference between preemptive and non-preemptive. Shortest the job first. Okay, so you can usually provide less the average waiting time and very good the response time. Problem? Nobody asked the question actually so far. How do I know CPU burst time? Do you know how long it takes when you execute your process? Sometimes, even though it's the same process, the same job, but depending on operating system status, it takes longer time, it takes less time, right? So, which means it's very hard, even sometimes impossible, to know CPU burst time at the beginning. Then, how do we consider such the algorithm without such information? Arrival time, first come first serve is okay because we know arrival time. But the shortest job CPU burst time, it's not possible to know exact 100% exact the CPU burst time, but it may be possible estimate using history, experience. Okay, generally. So we discussed about one of the main tasks of operating system is accounting information. Accounting information keep all the status about each process. Using that, even though it's not accurate, but we can estimate, judge, or predict the CPU burst time. So for that estimation, there are several algorithms, including Kalman filtering or others. This is the exponential, the averaging. Idea is very simple actually. So we are going to decide, estimate the next time slot CPU burst time. Okay, how? Based on the previous status. So this alpha and 1 minus alpha is the weight. Okay, we'd like to adjust the weight. So for example, this is the current. This is the previous. This is a previous, this is n plus 1. This is a previous, the CPU burst time. Then whether this, for example, if it need more CPU time, gradually, so this one will be increased. Okay, time will be increased. Otherwise, if the CPU burst time less and less, this one will be less. Based on the previous time, the slot information based on the experience. So you can adjust this one. So using this idea, so if this is the real This is a real the CPU burst time, but we can adjust like this way, the getting close. So this is will be addressed by estimation. Okay. So this is an example of how to use the exponential averaging. The next one is, instead of if the estimation is very hard for the CPU burst time, why don't we assign the importance of each process when process is started? When the process is enter the ready queue, why don't we assign the priority? So that is called priority scheduling. So there are also two types of the priority scheduling: preemptive, non-preemptive. Non-preemptive priority, it cannot be stopped. It should be, once the process is started, then it should be completed. That is a non-preemptive case. I gave the warning even a couple of times. Please, if you want to discuss with your friend in the classroom, you can leave. Okay? Do not bother the lecture. Please, I do not check the attendance, so please leave the classroom if you want to discuss with your friend in the classroom. Okay? So this is the priority scheduling. So in the priority scheduling, there are two types of the scheduling: preemptive and non-preemptive. We will see the example of that. However, any priority-based algorithm has the same problem. One is starvation. What is starvation? Depending on the priority. Okay, if I give the priority for the for example, we have the junior. Freshman, sophomore, junior, and senior in undergraduate. So if I give the priority for the grade, like the senior always the first, then followed by the junior and sophomore and the freshman. Then if I have all the senior student coming and again, no chance for the freshman. Okay, that is called the starvation. Starvation is not the problem of this scheduling, but it's a general problem. How can we address such a scheduling problem, the starvation problem? There are several solutions. One of the popular solutions of the starvation is, if freshmen wait 10 minutes but no chance to meet the professor, give the higher priority, which means the promote the status, like that you are sophomore, then consider as the sophomore student. Still no chance to meet the professor for next 10 minutes, then promote, upgrade the priority to the junior. Still no chance, finally senior, highest level. Okay, then eventually the student will meet the professor, that is called the AC. So you can, based on the how long the process is waiting, so you can give the higher priority. So this is a general solution in any priority-based algorithm. So we will see the example of the non-preemptive case first. I'm not going to use the Gantt chart again details. I'm going to quickly explain from now on. However, when you practice, when you are doing the homework quiz and also the project one, please first, before you start the coding, I know you are very good at coding, but solve the problem with your own hand by doing. Then next step is you can convert this one into your coding. So this is our process list. As you can see, so we have the priority. For example, P1 allowed the time 0, but it has a 3. Which one is the highest priority? 0 or 10? In computer system, 0 is always the highest priority. Windows use nowadays the current Windows system use minus even. It's just a shifting. Okay, so we can use the lower number as the higher priority. In this case, the process 3 is the highest priority. In case of non-preemptive case, at time 0, P1 will be selected, which means P1 will take all the CPU resources until the terminate. So that is the reason. Even though we have the P2 and P3 in the ready queue, with the higher priority, it will not take the context switch. it will take the CPU resource. Then we can calculate the waiting time. P10 and P2 is from here to, why P3 is selected? So P3 is a higher priority. Don't be confused. Mostly, always, in computer system, lower number is a higher priority. Okay, so that means P3 has a higher priority than the P2. So that is the reason P3 is selected and take all the CPU resource until terminated, and P2. Then we can calculate the average waiting time. In case of a preemptive case, P1 is the first time selected, but time 2. So time 2, P2 is allowed to compare their priority. Which one is the highest priority, higher priority? P2. So that is the reason P2 is selected. And P3, when P3 is aligned to the ready queue, so we need to calculate we need to consider the priority again. So P3 is the highest priority. So P3 will be selected until terminated because there is no more. If you have another process followed by this one, then calculate the same algorithm. Select highest priority. Then until 11, then P2 and P1, this is a higher priority. P2 will be selected. And finally, P1, we can calculate the same waiting time. Okay? We cannot guarantee the waiting time. It depends on the better waiting time. No, because it will be based on the priority. Okay? The next one is, so still, we need to, in this case, we have only 3 processes. Okay? Even though we have the preemptive cases, so 1, 2, 3, 4. But what if we have the many processes? And the duration of it takes a time for a lot of context switch. Okay? And also, the algorithm should be running for the every time. So that's overhead to address that problem. And also, depending on the algorithm, it takes a longer time. So instead, why don't we first segment the CPU time and assign based on the ready queue for each. Then at this time, this short duration of time, this piece, that is called the time quantum. Time quantum, there's no general size of the time quantum. It can be small, it can be larger. So we will see what is the characteristic of the shorter and large, the quantum of the round robin. So then, for each the time quantum, we can assign the process next from ready queue. In case all of the process in the ready queue get the chance for the first, then go back to the first process. That is called one round, and next round, because of that, is called the round robin the algorithm. So we will see the example. So at this time quantum is 20. So we are going to divide the time slot by 20. What if in the middle of, so for example, this is a time quantum 20. This is a 20, 40, 60. But process has the CPU burst time 10. What about this one? There are 2 options. You can start next time quantum right after termination. Okay? Or you can wait until the end of time quantum. Each one has benefit and pros and cons. Okay? For example, in this case, the first case, you can maximize the utilization. On the other hand, the second option, you don't have to worry about the interrupt or any signal or communication. Just every 20 time slot, you can select the next one. In our case, we will select the first option, which means if we stop before the end of time quantum, we will maximize the utilization here. So these are the process list process state P1. Do we need arrival time? Yes, we need arrival time, but in this case, we regard all process are in the ready queue. Okay, so we have the 1, 2, 3, 4, in this order, 4 processes with the CPU burst time 53, 17, and so on. So first, P1 is selected. Then take the first time quarter and remainder time is 33. Then next P2 will be done. Then it will end at 37. So we will take the next time quarter from 37. This one is the next one. And the P4, next one. And so this one is done. Go back to the beginning of the queue. That is a P1. And P1 takes the 33. Okay, that will be on that 33, the 13, so 20. The next one is the 28, and next one is done. So that is a 121, and so this one is done. Next P1 is a 13, and next 30, 28 still, 8 remainder. So P3 will take the only 8 time slot. Any question? What about the response time? This will be one of the best response time. Why? All processes will be selected at least one time within one round. So it will provide the best response time. Okay? So because of that, this round robin used in a lot of the operating system schedule. Okay? However, depending on the quantum size, the larger is the better? No, we cannot say larger is the better. The smaller is the better? We cannot say smaller is the better. What is the problem of the small time quantum? Context switch a lot. Okay, that is a problem. What about the large one? It will be the same as actually first come, first serve. Okay, so because of that characteristic, actually, you don't have to implement the separately. Using the round robin, you can, by changing the quantum size, you can implement the first come, first serve the same time. So this is the quantum size and versus the percent cost. Okay. Then next, what time is it? 55. 10:55.
10 minutes above.
Oh, it's over? You should let me know. I ask you. No. He's not here today. Okay, so next class we will continue the multi-level queue, and that will be part of your midterm exam also. That is the topic of your project 1. We will discuss a little bit more about the midterm and the project 1 after we finish this chapter. Any other question? Okay, thank you, and see you next.